Hey there.
Hey, how's it going, Freddie?
It's going all right. How about you?
Yep, it's going all right. It's going all right. Students are really struggling with logarithms in pre-calc. I
Yeah.
don't remember this problem last semester, but I also think I kind of breezed through the more conceptual stuff last semester. So,
I see.
yeah,
Yeah, I mean, I'm teaching calc now and we're
yeah,
doing derivatives of exponentials and logs. Like we kind of just did that and I like make it a point to really remind them what the hell a logarithm is
yeah,
because
yeah.
they don't know.
Nobody told them that last semester for sure.
Well, no, I mean, someone probably did or at least
Well,
tried, but
yeah, please try. Yeah, exactly. Yeah,
it doesn't stick.
yeah, yeah.
It's the best thing is like I have a couple, actually I have a few. I have like 3 or 4 students who I had last semester since I just taught pre-calc. And it's fun to be like, "Hey, you remember this, right?" And clear like I know they don't, but
You call them out. Yeah, that's
yeah, yeah.
yeah, that's fun.
What's the natural log of E, guys? I know I taught you this.
Yep, yep. How's it going, Hayan?
Going fine. How
Yeah,
are you?
doing all right. I forgot to ask you, how was the oral exam?
It's okay. So there are some questions I cannot answer, but I got some suggestions.
Yeah. Did you pass then, I assume?
Yeah.
Good, good. Glad to hear that. Did Dino ask you the about your favorite theorem?
I prepared it, but he didn't ask.
Oh.
Which one was it?
The one about your favorite, prove your favorite theorem.
Yes, but which was your favorite theorem?
For me, I prepared the class group is finite.
Nice.
Such a nice theorem. I mean,
Yeah.
I can see that.
Yeah, I think for me, my favorite theorem that I did was Dedekind-Kummer, and so I proved that one in the oral exam. That was fun.
Yeah, that's a nice one.
Hello.
Ooh.
All right. Did I forget to upload Monday's video? Well, if I'm asking, I guess I didn't forget, but I feel like I might not have uploaded Monday's video yet. I will look back. I will be sure to upload today's video today. So I'll look back and do that. Any questions? So if not, yes, I think this is going to be the last lecture, which is not on local class field theory. That's a weird way of saying it. In the next lecture, we'll actually start talking about local fields headed towards local class field theory. Yeah, and so in this lecture, we're still talking about the Brouwer group, which on the one hand, I mean, it is just the second Galois cohomology. The Brouwer group of a field, among other things, is second cohomology of the absolute Galois group with coefficients in the multiplicative group of the field. So it's a very natural piece of Galois cohomology. It also has a non-cohomological interpretation as isomorphism classes of finite dimensional central division algebras over a field, which makes it very important. I mean, there's an entire branch of non-commutative algebra where people study finite dimensional division algebras over a field, and the Brouwer group is the main object there. So that's certainly interesting in and of itself. And if that were not enough, the computation of the Brouwer group of both a local field, which we will do today, and of a global field, which is more complicated, these enter into local and global class field theory in important ways. Okay, so it's pretty well motivated that we want to study the Brouwer group. So okay, so today I'm going to give you some further properties of Brouwer groups, and then when it comes to computing the Bauer group of a local field, I really like Sarah's take on it. I think for the first time this semester, I was like, oh, let me just look back and follow Sarah's local fields, rather than what Harari does. And so the last main result that I'll do is I will compute, following Sarah, I will compute the Bauer group of any complete discretely valued field with perfect residue field. Okay, and so the case where the residue field is finite is the case of a local field in the sense of our course local class field theory, but and I think, in fact, really understanding the case where the residue field is finite, will be necessary in order to do the class field theory. But I think it's interesting, as you'll see. It in particular, it shows that the result is going to imply that there's lots. If you take any perfect field K, you could just take the Laurent series field over K, and that would give you a complete discrete valuation field with perfect residue field. And so so you have lots of choices of K in this way. If you take K equals Q, for instance, so if you looked at the Laurent series field over the rational numbers, we'll see that the Bauer group of that field is pretty big. Okay. And so in particular, whereas before the two examples that I gave you, I guess it's time to share the screen again. All of the examples that we've computed so far, so we computed, and then I gave you this exercise. What happens when the Galois group is procyclic? Well, the answer is that the Bauer group is always trivial unless the Galois group has order, absolute Galois group has order 2, equivalently if the field is real closed, in which case the Bauer group has order 2. So far we've been seeing examples of Bauer groups that are either trivial or have order 2, but if you pick a field at random, the Bauer group is probably a infinite discrete group with infinitely many elements of any order. Okay, and so the theorem in particular gives examples of that. All right, let's see. I think this is as far as I got last time. So I mentioned, I think at the end I mentioned that when I was taking the Galois cohomology of the Artin-Schreier isogeny, I only wrote down the consequence for the first Galois cohomology of Z mod PZ, which admittedly is the most interesting one. But if you do the higher Galois cohomologies, then you simply find that Galois cohomology for a field of characteristic P, Galois cohomology with coefficients in Z mod PZ is trivial for all Q greater than or equal to 2, which is kind of surprising, I think. So in particular, this is telling you that, to link this with, maybe I said this last time, I can't remember, but to link this with what we were talking about before, this says that if you take a CeLO P subgroup of the absolute Galois group, then that field in characteristic P has cohomological dimension at most 1, because if you have a pro-P group, you can check the Galois cohomology just by checking the largest non-vanishing index here. So again, often there's something funny about Galois cohomology of there's something funny about P primary stuff in characteristic P, and this is an instance of that. Okay. And then a closely related exercise is to show that if K is perfect of characteristic P, then there's no P torsion, equivalently no P primary torsion in the Bauer group. In fact, most of the fields of characteristic P that we are interested in, like local fields of characteristic P and global fields of characteristic P, have lots of P torsion in their Bauer group and therefore are not perfect. Okay. So so let's move on. There's a funny there's an amusing proof here that Harari gives about C1 field. So C1 field is something in it's a Diophantine properties of fields. It's kind of, I don't know, it's somewhere between arithmetic geometry and field arithmetic. So a field is C1, okay, not the greatest name we ever had, but there it is. If whenever you have a homogeneous polynomial in more variables than the degree, well, if it's homogeneous, it's always 0 at 0. C1 means you always have a non-trivial 0. Okay, so a homogeneous polynomial defines a hypersurface. Not necessarily nice, it could be singular or something, but at least, you know, geometrically that's what's happening. And so this is saying that a field is C1 if whenever you have a hypersurface you know, of small enough degree compared to its dimension, then it automatically has a rational point. Okay, so for instance, this is over a C1 field, a quadric hypersurface, so something defined by a quadratic form, will have to have a non-trivial, we'll have to have a point in projective space as soon as, in fact, as soon as its dimension is 1, which is the same as saying as soon as the number of variables is at least 3. Okay, and so one result along these lines, there are some nice classical theorems telling you that certain fields are C1. One such theorem is a theorem that I enjoy. The Chevalley-Varning theorem is a stronger result about polynomial systems of equations over finite fields. But again, if you just look first Chevalley and then Varning, and I'll let you look at this on your, you know, on your own time. But whatever Chevalley's theorem says, the fact that a homogeneous polynomial over a finite field in more variables than its degree has a non-trivial 0 is clearly a special case of Chevalley's theorem. And so in doing this, Chevalley was it was conjectured by Dixon and Arden that finite fields had this C1 property. And that conjecture was open for a while. I can't remember, I used to know, maybe between 10 and 20 years. And then Chevalley came with this kind of beautiful, like 2 or 3 page proof. And then Varning came along with like a 10-line proof or something. Okay, so finite fields are C1. We'll see later why we care about that. There's a nice theorem of Chen, who was a Chinese mathematician who came over to the United States to do his PhD thesis under Emil Artin. So Chen's theorem says, if you have a function field, or if you have a field that has transcendence degree 1 over an algebraically closed field, so for instance, the function field of a curve over an algebraically closed field, then such a field is C1. Again, I'm not, there's a lot of nice facts about C1 fields. Maybe I should say there's a nice little textbook about this, or text. So it's from the 60s, I think. So it's by Marvin J. Greenberg. And it's called Lectures on Forms in Many Variables. And so just, you know, all these results, there's something called CR. So there's weaker conditions that a field may satisfy, and so he studies CR fields. Okay. So you can find these results in that.
Can I ask also how would somebody prove those theorems? I don't see what somebody can use.
How would somebody prove the Chevalley-Varning theorem?
Yes.
Yeah, well, I have like a whole book about generalizations of the Chevalley-Varning theorem. So yeah,
I can look at that, but I was just wondering what is the basic idea, or how do you? It just seems like a problem. I don't know. It just seems that you don't know where to start.
Well, it was an open conjecture for about 10 years. Chevalley's proof uses the relationship between polynomials and polynomial functions. I guess I'll give you, where do you start? You start so if I have a system of polynomials, F1 through FR, those are doing something more general, I guess. This is the basic observation. This is Chevalley's observation. Then, and you have X in FQ to the N, then X is a simultaneous 0 all of these polynomials, so, as the FQ rational point of the corresponding affine subvariety, this happens if and only if the Chevrolet polynomial attached to X is equal to 1. And so what is the Chevrolet polynomial? This is the product from J equals 1 to R of 1 minus Fj to the Q minus 1. Okay, so if you just look at this, this is not a profound statement at all. I'm saying that if all of these evaluate to 0, then the product evaluates to 1. If any one of them evaluates to something which is not 0, then I raise it to Q minus 1, I get 1, the product is equal to 0. And so the idea is that this polynomial is basically the sort of the FQ valued characteristic function of the 0 set of F, the 0 set of the polynomials. And that's how you get started. All of a sudden, you've changed the statement about the number of zeros of the variety into a statement about when this associated function is not equal to 0, and then Chevrolet uses the relation between polynomials and polynomial functions over a finite field. So that's a proof. Again, I'm sure I can show you. Oops, you can't see that. So I'm sure, and I have many papers of mine, so I can refer that to you. And then an even quicker proof was done by Axe in the 60s. And yeah, so that's how these arguments get started. But yeah, it was pretty exciting when you did it the first time. Sure. Yeah, so there's several proofs. Anyway, I can send you a surprisingly long file of information about.
I can find them if it's on your webpage. I can find them and I can read them.
Well, the one is not on my webpage actually. It's secret. But if you send me an email, I'll send it to you. Yeah. Anyway, yeah. So Axe, among other things, gave a 10-line proof of even a stronger version than this theorem, and his proof uses surprisingly little. Yeah. Okay.
If I remember correctly, I think Aaron gave that proof in a mock AMS talk.
Yeah. Okay. Good. Yeah. No. So it's a little ridiculous how short the proof is. I mean, okay. I think. Oh, yeah. Actually, a reference is my undergraduate number theory notes. I definitely talked about the Chevrolet product theorem in my undergraduate number theory notes. Yeah. Okay. Right, and so then Shen's theorem has this. It's also true, by the way, that an algebraic extension of a C1 field is also a C1 field. That's not. In fact, I think even that's even proved in Harari. So Harari shows. Okay, so this is an interesting class of fields for sure. This kind of idea that low degree hypersurfaces should have rational points is a priori interesting if you're interested in rational points on things. Okay, right. Okay, so these are some of the basic results. So Shen proved that function fields in one variable over an algebraically closed field are C1, and then Lang, this is coming out of his 1952 PhD. This is all kind of coming from Arden, a lot of it. So both Chen and Lang were students of Emil Arden. And I think the idea of a C1 field is actually due to Arden. Okay, so Lang proved that if you have a complete discrete valuation field with algebraically closed residue field, then K is C1. He actually proved more than that, and so I'm going to use the more than that at some point later. This lecture is gonna take longer than I'm thinking. So in fact, he also proved that if K is a complete discrete valuation field, then the maximal unramified extension of K is C1. Okay, and so the idea is that like this kind of almost but not quite, the residue field is going to be, with perfect residue field still. So if K is a complete discrete valuation field with perfect residue field, then the maximal unramified extension is C1. For a second, it looks like this might fall under the result that I said before, because since the residue field is perfect, in general, the residue field of the maximal unramified extension of a complete discretely valued field would be the separable closure of the residue field. But since the residue field is perfect, that means that the residue field is algebraically closed. The problem is that probably the maximal unramified extension of K is an infinite degree algebraic extension of K. So it's not complete anymore. It's something called Henselian, but it's not complete. And so there's some fine print here. Basically, he argues that the completion of the maximal unramified extension has vanishing Bauer group, and then argues from that the unramified extension has vanishing Bauer group. Okay. Oh, shoot, I should have just read. So yeah, so this theorem that if K is C1, then so is every algebraic extension. So I put that up here as well. And then one reason why we care is that this C1 is a Diophantine condition on the field, right? Which implies that the Bauer group vanishes. Okay, and so I want to prove part A is it's really like a paragraph. It's no big deal, just from the definition of C1. This is interesting. So I'm going to give Harari's proof, which is a funny application of this like Tate Nakayama type stuff we were doing before. I should say that on the division algebra side, this statement is much more clear. And so I do have some notes on non-commutative algebra from a summer half course I taught a while ago. That's on my page of expositions. And I believe in those notes, you'll get I develop there's something called the reduced norm on a division algebra. And if you know what the reduced norm is and its most basic properties, then you will immediately understand why a C1 field will have vanishing Bauer group. But okay, so now I want to do so I want to use, this is Harari's proof, which uses a theorem of Galois cohomology. So okay, or group cohomology. So let L over K be a finite Galois extension of degree D. Okay. We know that the Bauer group is the direct limit of the Bauer groups over the finite Galois extensions. We proved that before, so it would certainly suffice to prove. In fact, we know that it's the injective direct limit of those things. So as I said before, it is necessary and sufficient to prove that the Bauer group of every finite Galois extension L over K is trivial. Okay, so I'm going to look at the norm map, and so I guess I'm going to say this pretty quickly, but if you stop and think about it, if you just, the norm map is really the determinant of multiplication by L viewed as a K-linear map. Yeah, and so if you have if you just choose a K basis for L and just kind of put variables in play, and you write an arbitrary element of L as kind of a formal linear combination of elements of the basis, and then you take the norm, then sooner rather than later, you'll discover that the norm map in a degree D field extension can be viewed as a homogeneous polynomial of degree D and D variables. I mean, for instance, the norm from like C down to R takes x plus iy to x squared plus y squared. So it is indeed a homogeneous polynomial of degree 2 and 2 variables. It's not so surprising. Okay, and so for any element alpha in K, let me look at the equation non-zero. Let me look at the equation norm of some undetermined element x in L is equal to alpha times x0 to the d. Okay, so I'm adding one more variable, right? And so now I have a homogeneous, this thing minus this thing is a homogeneous polynomial of degree d in d plus 1 variables. Okay, well, if my field is C1, which is exactly what I'm assuming, then this equation has a non-trivial 0. Okay, that just means that one of the coordinates, so this x you think of as corresponding, once you coordinatize L as a k-vector space, you can write x as x1 through xd. Well, if x0 is equal to 0, then the norm would be 0, but in a field, hey, the norm is only 0 when the element is 0. So if x0 is 0, then also x would be 0, the whole thing would be 0. So therefore, since the solution is non-trivial, x0 must not be equal to 0. x0 is an element of k, so you can bring that inside. The norm of any element of k is just that element to the dth power, right? It's the product of the Galois conjugates. And so therefore we did find that the norm map is surjective, because if x0 is non-zero, then the norm of x divided by x0 is going to be equal to alpha. Okay, so what did that show? That showed that in a C1 field, the norm map is surjective on any, we didn't use that the extension was Galois here. So the norm map on, that's all we need, but the norm map is surjective on any finite extension. Okay, that's kind of interesting in and of itself. Anyway, so we combine with Hilbert 90, right? So Hilbert 90 tells us that H1 of this Galois extension with coefficients in L star is equal to 0. That's exactly on the nose what H1 says. Here, L over K is a finite Galois extension. What about H0? H0 was, was the co-kernel of the norm map, right? Tate H0 is K star modulo the norm of L. So if the norm is surjective, that's telling you that Tate H0 is equal to 0. And now you say, oh, okay, also, because algebraic extensions of C1 fields are C1, you can do the same thing for any subgroup here. So in other words, if instead of L over K, I went to K prime, well, okay, well, K prime is an algebraic extension of a C1 field, so K1 is still, K prime is still C1, L over K is still Galois, finite Galois, that's the way finite Galois extensions work. The exact same argument would tell us that that the H0 and the Tate H0 and the Tate H1 vanish for every subgroup of the Galois group of L over K. Okay, that's how Galois theory works. In particular, it tells us that all the CELO subgroups vanish. And now, actually, this rings a bell. There's a big theorem from chapter 3 in the notes, which I can flip back and show you, which says precisely that if you have two consecutive vanishing Tate cohomology groups, when you pass to, sorry, I'm having a little trouble finding it. I think I confused myself because I stated Tate Nakayama and then went back. No, hold on. I'll find it. Cut products, cut products, products. Where the F is this there? Here it is, found it, okay. So you have a finite group and you have a G module, and suppose that you have two consecutive indices in Tate cohomology, so that the Tate cohomology vanishes, not for the group itself, but for all the CELO P subgroups. Then the conclusion is that the module is cohomologically trivial. So it's totally acyclic for Tate cohomology of all subgroups. Okay. And so that it's kind of funny. This really is amusing. This is not the standard way around to do this, but it works, and I kind of like it. So by that theorem that we stated before, we're precisely in a situation to assert that as the G of L over K module L star is now totally is now G of L over K cohomologically trivial. Okay, so if it's odd of L over K cohomologically trivial, then in particular the second cohomology is equal to 0. And that is the Brouwer group of L over K being equal to 0. Okay, so that I find this this is a more complicated proof than you need to do if you understand the Brouwer group on the division algebra side, but it's interesting. It's interesting that you can do this. Okay, and so as I said, this is a fun proof. The result is actually easier to prove on the division algebra side. Okay, so one consequence of this, again, so every C1 field has vanishing Brouwer group. So in particular, Chevalley proved that finite fields are C1, and so that gives a second proof that the Brouwer group of any finite field is 0, because, well, a finite, you can think of Chevalley's theorem among other things as being a sharpening of the fact that the Brouwer group is equal to 0. Again, if you think about it in terms of division algebras, the Brouwer group being equal to 0 is telling you something about, well, in fact, if you look at it right here, yeah, I guess I'm skipping this. There's a result that says that in general, the vanishing of the Brouwer group is equivalent to the search activity of the norm map over all finite Galois extensions. And so, okay. That's the way that we proved that the Brouwer group of a finite field was equal to 0 before, was taking advantage of the fact that the norm map was search active. Okay, so that's nice. And so my next goal, so for the remainder of this lecture, we'll see if I can get through it. I'd like to. I'd like to prove that if I have a complete discrete valuation field with perfect residue field K, then the Brouwer group of the field is isomorphic to the Brouwer group of the residue field, direct sum that what's chi or x of k. This is the character group. By the character group of a field, I mean the Pontryagin dual of the absolute Galois group of the field. Okay, so it's so the Hom from the absolute Galois group into Q mod C. Continuous on the box. Okay, so we talked about this character group before. So in other words, this chi of k is the discrete torsion group that is Pontryagin dual to the Galois group of the maximal abelian extension. Okay. So in other words, the character group is the character group would be trivial if and only if the field had no proper finite abelian extensions. Okay. All right, so that's a nice result. And then in particular, the case that we, as I was saying before, so for instance, if you take K to be Q double bracket Q Laurent series field over Q, then you're going to get that the Brouwer group of the Laurent series field over Q is isomorphic to the Brouwer group of Q. Well, you don't need, hopefully by the end of the course, you'll know what the Brouwer group of Q is. That's a pretty big infinite group as well, but forget about that at the moment. It certainly has inside it the character group of Q, and of course, the maximal abelian extension of Q has infinite degree over Q. In fact, of course, for any n greater than or equal to 2, there are infinitely many abelian extensions of degree n of Q. And so this character group of Q is a torsion group that has infinitely many elements of order n for all of it. Okay? So therefore, the Brouwer group of the Laurent series field over Q is big group. Okay, but again, the case of most interest to us is when the residue field is finite. Well, that simplifies matters considerably. We just proved for a second time that the Brouwer group of a finite field is equal to 0. Indeed, it's a C1 field, among other things. And so therefore, the Brouwer group of so if you take any complete discrete valuation field whose residue field is a perfect C1 field, then the Brouwer group is isomorphic to the character group over the residue field. But again, so that therefore the character group of FQ, right? So we talked about this. So that's the Pontryagin dual of Z hat, which is the Galois group of Q. And so just as Z hat is the inverse limit of Z mod NZ, its Pontryagin dual is the direct limit of Z mod NZ. So that's Q mod Z. Okay. And so yeah, so in this case, I guess it's important that in general, this isomorphism is non-canonical. There's something is split, but non-canonically in order to give this isomorphism. But in the case when this factor just disappears, I guess it should follow from the proof that you get a canonical isomorphism from the Brouwer group. Okay, so that's what I want to prove. Any questions? It's good. This is a cool theorem. It's certainly the most exciting theorem about Brouwer groups we've seen in this course by far. Any questions before I start proving it? Okay, so fields can have big Brouwer groups. You heard it here first. So yeah, there's various steps. So first step, right, so if I take any Galois extension so that the Brouwer group over that extension is equal to 0, then we can identify the absolute Brouwer group of K as the relative Brouwer group. And this is true because the Brouwer group of L over K, which you would have, a priori was defined as the, as Galois cohomology of the Galois extension odd of L over K, in this particular case was identified with the kernel of the restriction map. And so, okay, if the Brouwer group of L is equal to 0, well, then the kernel of a homomorphism into the 0 group is everything. Okay, so that's certainly true. And now I'm starting off actually by using this. You could do better than this, or you could ask for more details on this. So here I'm going to use this theorem of Lang that I mentioned before. That so the K on RAM, I have a complete discrete valuation field with perfect residue field. I told you that Lang proved in 1952 that the maximal unramified extension was a C1 field, and therefore, by what we just proved, has vanishing Brouwer group. If you didn't want to prove the C1-ness and you just wanted to prove that the Brouwer group of K on RAM was equal to 0, there would be easier ways to do that. But for the moment, let me just go with the sharper thing. Okay, so again, there's a theorem 12 and a 1952 paper of Lang from his thesis. And so we do get that the Brouwer group of the maximal unramified extension is equal to 0. What is this telling us? This is basically telling us that any cohomology class in the Brouwer group is split upon restriction to the maximal unramified extension of K. In fact, if you wanted to interpret this in terms of division algebra, this would prove that any division algebra has an unramified splitting field, if that means something to you. Okay, so the Brouwer group is therefore the Brouwer group of the up to the maximal unramified extension, and then we take limits, right? As usual, we take these limits, and so really, what do I need to do? It will be enough if I take a finite Galois unramified extension of K. That's pretty nice, right? Finite Galois unramified extension of a complete discrete valued field. So if I can compute the Brouwer group of that, then I just take the limit, and that gives me the Brouwer group of K. Okay. All right, and so one point being that let little l be the residue field of capital L, let little k be the residue field of capital K. We're doing local field stuff. Because the extension is unramified, that means that the Galois group of the extension is canonically identified upon reduction modulo the maximal ideal with the Galois group of the residue extension. Okay, so that's a big part of the proof. So we can identify the upstairs Galois group L over K with with the Galois group of the residual extension. This is the characteristic property of unramified extensions. Right? Okay. Right. You know, in general, this would just be like a subgroup of the Galois, or in general, it would be a quotient group of the Galois extension, and then the inertia subgroup would be the kernel. But since it's unramified, there's no kernel. Okay. So now, also because the extension is unramified, so I have a z-valued valuation on k, right? That's what it means to be discretely valued. In general, I can always, you know, extend a valuation to, I mean, whatever variable is just a finite degree extension. That's nothing. So in number theory 2, we talk about extending valuations, right? In general, if you literally want the upstairs valuation to extend, to restrict back to the downstairs valuation, then the value group might enlarge depending upon the ramification index, but hooray, it's unramified. And so therefore, in fact, there is a unique extension of this valuation to L star, and that's z-valued as well because it's unramified. Okay. If its ramification index was E, then the unique extension would have values in 1 over E times Z. Okay. And so now we have an short exact sequence of, so G is the Galois group of L over K, which we can identify with the Galois group of the residual extension. So this standard exact sequence, just by taking, just take the valuation as a multiplicative to additive map. Its kernel is what it is. It's the unit group of the valuation ring, kind of by definition. And so this exact sequence is an exact sequence of G modules. If you think about it, the valuation of the way the extended valuation is defined makes immediately clear that the valuation of X is equal to the valuation of sigma of X for all Galois automorphisms, and so that's basically what you need to know in order to know that this map is Galois equivariant. Okay. Now I choose a uniformizer in my downstairs field K, but for the third time in the last 5 minutes, hooray, the extension is unramified, which means precisely that my downstairs uniformizer is also an upstairs uniformizer. Again, that's what unramified means. And so therefore we get a splitting. In general, we would have had this splitting just as a short exact sequence of groups. So to split this guy, I mean, of course I have a splitting in some sense because this is a free Z module. So a splitting just, you know, you take one and you map it, you map it back here. So if you think about it for a second, literally the splittings of this surjection correspond to uniformizing elements of L, okay, which exists. But I want the extension to be split. I want this map, this section map, also to be GK equivariant. And so what does that mean? Well, this has the trivial G module guy. So I want a uniformizer which is fixed under the action of Galois. Well, great. That's why I took a downstairs uniformizer pi that will be fixed under the action of Galois. So everything works out great. And so yeah, so therefore, as Galois modules, you get L star is isomorphic to the unit group of L cross Z as the value group. Okay, well, why is that helpful? Well, that means because we're trying to do Galois cohomology with coefficients in this guy, and this guy is the direct sum of 2 other guys. So everything in sight is going to decompose non-canonically as the direct sum of Galois cohomology with coefficients in this one, direct sum Galois cohomology with coefficients in this one. Okay. So that's what I just said. So, all right, I just said it. So therefore, really, we've reduced our problem for 2 easier problems. I want to compute these 2 Galois cohomology groups for each finite degree unramified Galois extension L over K, and then I want to pass to the limit. Okay. One of these 2 is easier than the other. The Z is pretty easy, so let's do that one first. So for Z, all I'm going to use is this. I mean, you can't argue with this. This is a short exact sequence of G modules with just trivial G action. Can't complain. And here's a little exercise though. If you take any profinite group and any G module that is a Q vector space. Okay, so the way to say this is that it's uniquely divisible. Multiplication by n is bijective for all positive integers n. That's the same as saying that it has a canonical Q vector space structure. Then anything which any G module whose underlying Z module is actually a Q vector space is going to be acyclic for group cohomology. Okay. This is not a hard exercise. Basically, the idea is that you reduce to the finite case, right? And then the idea is, I think I had another exercise about this. If instead of a ZG module, you have an RG module for some other commutative ring R, then you track everything through the cochains and you get that the cohomology groups still have an R module structure. And so therefore, these cohomology groups still have a Q module structure, but they're also torsion groups. So torsion Q vector spaces are probably 0. So that's okay. That's pretty much how you do the exercise. Okay, and so what's the point? Well, the point is, well, you know, if this guy is acyclic for cohomology, that's going to tell us what the Galois cohomology of Z is in terms of the Galois cohomology of Q mod Z. So if you just do if you take the connecting guys, so you're going to get 0 is going to go to H1 of here. Connecting guy is going to go to H2 of here is going to go to 0. So therefore, H1 with coefficients in Q mod Z is going to be canonically isomorphic via the connecting map to H2 with coefficients in Z. Okay. And so H1 with coefficients in a trivial module is just continuous homomorphisms, and that is the character group. Okay. So we found that for this, so what did this show? This showed that for any profinite group G, H2G of Z is canonically isomorphic to the character group of G. Okay, good. And so we can certainly pass to limits on that. And so if we pass to limits, in this case, I gave you a cautionary tale about passing to the limit. You should think about it, but it works well. And so now I'm just passing to the limit from the character group of the finite quotients to the character group of the entire unramified Galois extension. And so if you pass to the limit, indeed, you get the character group of the Galois group of the maximal unramified extension of K over K. And as I said, because the residue field is perfect, the Galois group of the maximal unramified extension upon reduction is canonically identified with the absolute Galois group of the residue field. Okay, so that was sort of half of it. We did identify this factor of the Brouwer group of the local field as real, you know, if you like, the character group of the maximal unramified extension of K, but, you know, it's probably more helpful to say that that's the character group of the residue field of the, yes. Okay, so now what about this unit group? This one is a bit more interesting. And so here's a fun lemma from Serre. So suppose G is a finite group. Suppose I have, this keeps going. Suppose I have a decreasing filtration of G modules. Okay, so in other words, it's exactly what it sounds like. M1 is a G module. It's contained in M2, which is a G module, etc. Okay, decreasing filtration of G modules. Serre says things in his inimitable Bourbakistic, slightly fancy way. So he says, suppose that M1 is complete and separated for the topology induced by the collection of subgroups. Okay, that makes sense if you like to think about those types of kind of adic topologies. In other words, I can put a topology on M1 so that a neighborhood base for the identity is given by all these subgroups. And then a neighborhood base for any other point is given by the cosets of those subgroups. So that defines a, makes M1 into a topological commutative group, and it makes sense to ask whether it's complete in that topology. Maybe it's a little bit unnecessarily fancy, though. A more algebraic way of saying that is that there's a natural map from M1 to this inverse limit, right? I keep modding out by larger and larger n, so I keep modding out by smaller and smaller submodules, and so I certainly have, because I have a map from M1 to M1 mod Mn for all n by the universal property of the inverse limit, I have a homomorphism, and to say that M1 is complete and separated for this topology means that this natural map is an isomorphism. That's what I'm assuming. Okay, so M1 is some kind of M1 is some kind of completion of with respect to these quotients. Okay. All right, I'm still stating something. That was my hypothesis. So now, what is this? This is some kind of Davy-Sage result. This is saying that if the group cohomology of the successive quotients is equal to 0, then the group cohomology of the whole thing is equal to 0. That's what this lemma is saying. Okay, and this is a fun proof. I mean, the question is where is this topological sort of where is this topological assumption being used? The idea is somehow by successive approximations, we will push our difficulties off to infinity. Okay, so it's a nice proof. Kind of direct proof. So I take a cocycle with values in M1. I'm trying to show that my cocycle is a coboundary. That's what it means to show that the cohomology is equal to 0. What do I know? I know that the image of this cocycle with values in the quotient is a coboundary. Okay, so what does that mean? If you think about it, that means that I have a Q-1 cochain with values in, is Tyler leaving? Yes. So I have a Q-1 cochain with values in M1, so that the idea is that phi is approximately the coboundary of psi1 in the sense that in the sense that, these two things are going to be equal in the quotient modulo M2. That's what we're assuming. And so therefore, when lifted back into M, what you can say is that phi minus d of something else is a cocycle with values in M2. Okay, so this is a nice argument. This is the successive approximations this is exactly what the hypothesis gives you. And then you say, I can keep doing this. Right now I have a phi1, which has coefficients in M2, but I know that the cohomology of M2 modulo M3 is equal to 0, so I say exactly the same thing at every stage. Okay, so I keep doing this. Continuing in this way, I get a sequence of, what do you call them? Cochains psi n and cocycles phi n, which keep doing this. So I'll just write it out. So we just did the first stage. The phi is equal to is the boundary of phi1 up to psi1 up to some phi1, right? And then I do the same thing. Phi1 is, that should have been a 2, is the boundary of some cochain psi2 up to some psi2, etc. And you keep doing this. Okay, and then you're like, all right, well, how do I compile this together? If you kind of the idea here is if you just keep using these equations, then you see that, like, if I compare phi to the d of psi1 up plus dot 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 plus psi n, if you just keep substituting these things into each other, you can see that psi1 plus dot 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 plus psi n is sort of an approximation to the guy whose d is equal to phi, which is what I'm trying to prove, in the sense that the difference is going to be phi n plus 1, which is in some larger and larger module. And then the fun part of the proof is that the completeness of M1 means, and I'll let you think about this either algebraically in terms of the inverse limit or topologically, if you have a complete, in fact, if you have a complete topological commutative group, you can talk about infinite series in the group because you have a topology. And so the completeness means that Cauchy sequences are going to converge. So again, you can do it topologically if you want, or you can just think about it in terms of being isomorphic to the inverse limit. So my claim, though, is that our completeness hypothesis means that literally we can make sense of the infinite sum of these psi n's, and that will be an element of Q minus 1 cochain with values in M1. I'll let you, again, think about it topologically or algebraically, your choice. And if that's the case, then we definitely win, because d phi 1 is equal to psi minus psi 1, d phi 2 is equal to phi 1 minus phi 2, etc. Again, I get this infinite series and this infinite series. Because M1 is complete with respect to this topology, each of these successive guys is getting farther and farther out, and really is converging to zero in some suitable sense. And there you go. So I built my co-boundary. In the end, I can see that phi really is the boundary or something. Okay, so that's that lemma, which is fun. And now, now we have the lemma that is going to compute the Galois cohomology of the unit group. Here it's more general. We only need the second Galois cohomology of the unit group, right? If you're following along, we kind of want the second Galois cohomology of the unit group to have something to do with the Brouwer group of the residue field. And this is exactly what we want to see in order to get that. So yeah, so I claim that for all Q greater than 1, if I take this finite, L is now the same as it was a little while ago, a finite Galois unramified extension. So the Galois group of L over K can be identified with the Galois group of the residual extension, little l over K. And then in fact, for all Q greater than 1, this Galois cohomology is equal to this Galois cohomology. And again, if you take Q equals 2, then this guy, because G is G of little l over K as well, this guy is the relative Brouwer group of little l over little k, and then passing to the limit, we would get what we wanted. Okay, so this lemma is the last piece of it. Okay, and so here, not for the last time, the higher unit groups which come up when you're studying local fields come into play. So for n greater than or equal to 1, by definition, the nth higher unit group is the elements of the valuation ring, so that the valuation of x minus 1 is at least n. You think about that for half a second, and you see that that's 1 plus the nth power of the maximal ideal. Okay, but these are subgroups. By definition, the 0th unit group should be. It doesn't quite work according to this definition, but if you ever see a UL super 0, it should be the entire unit group. Okay, so these are the higher unit groups, and then by a well-known result in number theory 2, so here's where you can find it in my notes, the successive quotients of the higher unit groups are naturally isomorphic to the additive group of the residue field. Okay, and in fact, so that's just true. That statement is if you have just one field. Here we have a finite Galois extension, and so I'll let you think about the fact that this known isomorphism is actually equivariant for the Galois action. Okay, so that's true. Also, U1 has this completeness property that occurred in this more abstract lemma of Serre. In the case that we really care about where the residue field is finite, U1, all of these higher unit groups are literally profinite groups. In other words, these successive quotients are all finite. And so the fact that U1 is isomorphic to this limit is really just expressing the fact that the higher unit groups are profinite groups. But if you think a little bit about what the completeness of the field means, you should be able to convince yourself that for any complete discretely valued field, the higher unit groups are complete with respect, the U1 is complete with respect to the topology induced by the higher unit groups. It really just comes down to the completeness of the field. Okay, so what am I saying? I'm saying that we can, I claim that we can apply the previous kind of abstract lemma with G to be the Galois group of this finite Galois unramified extension, and MI to be the ith higher unit group. Okay. Why can we apply it? Well, again, the Galois group of the capital L over K is canonically identified under reduction modulo the maximal ideal with the Galois group of the residue extension. But now this is very simple. We just have a finite Galois group acting on the additive group of the larger extension. Well, that's an induced module. We proved that long ago. So for sure, all the higher G cohomology of L plus is trivial. And so because L plus is isomorphic to this quotient of the unit groups, well then therefore all the higher G cohomology of these successive quotients are equal to 0, which was the hypothesis in this lemma of Serre. And so what should the conclusion be? The conclusion should be this, again, this holds, this Serre you do it 1Q at a time, but we have it for all Q greater than or equal to 1. And so therefore all Q greater than or equal to 1, we're going to get that the Qth cohomology of the first unit group is equal to 0. Okay. We didn't want the first unit group, we wanted the 0th unit group. Okay, so let's go back and compare how does the 0th unit group compare to the first unit group. Well, the first unit group is really just the kernel of this reduction map. They're the ones that reduce to 1 modulo the first power of the maximal ideal. So by definition, it's just the kernel of this induced map on unit groups. And so again, this is a short exact sequence of Galois modules. And so we just decided that the first higher unit group is acyclic for Galois cohomology. So if we take the Galois cohomology of this sequence, we are going to get that these cohomology groups are going to be identified for all Q greater than or equal to 1. For any Q, the Qth cohomology here is going to be 0. It goes into the Qth cohomology here, goes into the Qth cohomology here, goes into the Q plus first cohomology of that, which is also 0. So we get our isomorphism. Right, and that's what I claimed in the statement of the lemma, that the Qth for all Q greater than or equal to 1, the Qth cohomology of the unit group is isomorphic to the Qth cohomology of the multiplicative group of the residue field. Again, that was the statement of the lemma, and then again, just to you put it all together, you get that the Brouwer group is equal to the unramified Brouwer group is equal to this limit. At each finite level, we got the Brouwer group as the isomorphic. We did choose something there. I chose a uniformizer of K, and so we get it like this, and right, and so this one we identified we just did this. This one got identified with the relative Brouwer group of little L over K. This one got identified with the character group of the residue field K. And then you take the limit and you get the isomorphic to the Brouwer group of K, direct sum. The character group, and then, okay, one more time. If you have a complete discrete valuation field with finite residue field, then this Brouwer group vanishes, this character group becomes Q mod Z, and so we get that the Brouwer group of our local field is isomorphic to Q mod Z. Okay, so that's what I wanted to do. And again, this completes the Galois cohomology only part of the course. And so yeah. Let me do people have problems to solve on Friday? If not, it would be fine for me if we just broke on Friday. You could have a few days to think all this through, and then we can just come back on Monday and start talking about local fields. So is there anybody who wants to solve any problems on Friday? I didn't set it up so as to make people want to volunteer to do it, I guess. Yeah, so okay, so let's say that we won't have a Friday problem session this week, and then you can, it may be helpful to take a little bit of time to just go back over all this stuff. And then, yeah, we're going to be talking about local fields and their class field theory. And I think, in fact, I think a more careful discussion. We want the Brouwer group to be isomorphic to Q mod Z, but again, we don't want an abstract isomorphism. In particular, if I make a finite degree extension of my local field, I want to understand what happens to my Q mod Z. So I think we may have to go back over this a bit more carefully as the next thing that we do. Okay, but we made it to class field theory, so that's good. All right, see you guys on Monday then. Bye.